All right, so I want to do a video on quiz review number 1, and you're going to see a lot of similarities between this and the Brick Lab. So let's go ahead and take a look at this. It says a Blimpie Burger, which is a burger place in Ann Arbor. It used to be right by the Union in Ann Arbor and West Quad and South Quad on State Street, but then they moved it because U of M or Blimpie Burger sold the land, which was worth a lot of money, and then U of M built a, I think, what did they build there? I don't know if it was another dorm or if it was something, but U of M probably offered them a lot of money, and Blimpie Burger kind of went out of business for a couple of years. And now they have a new store, but it's not the same. It's in a different location, and it's kind of expensive. But the burgers are really good if you like greasy food, and French fries and the onion rings. And just make sure if you ever go in there, you don't order a single, because they usually won't give you one. The smallest you can get is a double, and that's kind of weird, but that's the size of the burger that is their single is their double. So yeah, you'll look like a rookie if you go in there and order a single. So you have to ask them for a double. And yeah, so anyways, there you go, a little Ann Arbor knowledge. A Blimpie Burger with all the best toppings is at rest on a dining room table. A smart dog is able to lift one end of the table with his paws to an angle of 30 degrees where the delicious burger just begins to slide. If the mass of the burger is 300 grams, we're going to need that. I'm going to highlight that. What is the normal force on the burger? So we want to know. This is the first thing we're going to have to, whoops, I thought that was highlighter. It's not. Let's undo that. Let's see if we can get some yellow highlighter. First thing, what is the normal force on the burger when the angle is 30 degrees? Second, what is the maximum force of static friction for the burger? Okay. And then finally, what is mu static max? Okay, so I think very similar to the Brick Lab. So let's go ahead and take a look at this. So the first thing they tell us to do here is draw a free body diagram and include components. So let's go ahead and sketch the burger. I don't know how to draw a hamburger with all the best toppings, but something like maybe that. Okay. And I guess I could, try and add a little more detail there, but you get the idea. And all right, so let's go ahead and put a dot in the center. I'll go ahead and do that in blue. And then we're going to have our forces coming from that central dot. So forces here. First one, force gravity, always down. So we'll go ahead and point that. Force normal, always normal or 90 degrees to the surface. I'm going to stick with purple here. So maybe something like that. It says that it just begins to slide. So the burger isn't moving. It's going to break equilibrium, but it's going to be in equilibrium up to that point that it just begins to slide. So we're going to consider it equilibrium, meaning that the forces will balance here in the X and Y direction, and the acceleration will be 0. But if it's not sliding down the ramp, we know that friction opposes motion, and the burger is going to want to slide down the ramp. So friction is going to point up the ramp. And we'll call that force, friction, static. All right. So there we have it. 3 forces on the Blimpie Burger, and that's it. There's no other forces in the free body diagram, right? But We're going to label some more here in a second, but technically there's only 3 forces. There's going to look like there's going to be 5 here in a second, but there's only technically 3. So just so you know. And it says, so draw the free body diagram. Those are the 3 forces and include components. So let's talk about why. So we're going to tilt the axis system. We'll call this direction positive y, negative y. We'll call a positive x up the incline and down the incline negative x. So force gravity does not agree with this new system. It points straight down, and therefore it needs to be split into components. So let's go ahead and get a different color here. I don't think red. Let's go with brown. All right, so I'm saying that a piece of gravity will oppose normal and point in that direction. We'll call this FGY. And then a piece of gravity will cause the burger to slide down the incline. We'll call it FGX. Notice FGY and FGX are head to tail to create the purple FG. And I'm going to go ahead and draw this angle right here. This is 90 degrees, always between FGY and FGX. And the angle of the incline, which I think is 30 degrees, 30-degree angle is let's see, is right here. And we can go ahead and write 30 degrees. This is going to be theta. That angle is also going to be in our triangle here. And it's going to be, let me see if I can write a 30 right there. Let's go ahead and highlight. It's going to be that angle right there. So you can see that that's going to allow us to do some SOHCAHTOA. Having this right triangle and knowing one of the angles. So across from 90 is always my hip, which is always going to be FG. Next, or across from 30 is my opposite, which is FGX. And next to 30 is my adjacent, which is FGY. All right. So far, so good. If you... Okay, so here's some reminders down here. It says, be sure to label FGX, FGY. We did that, and FG. Also label the hip, op, and adjacent, which we also did. Then they say label theta twice. All right, so theta is there once for 30 degrees. And we technically already labeled it here, but I'll go ahead and draw the symbol theta in right there. But you can see the 30 degrees is labeled twice. So sometimes I like to, this isn't part of what they're asking, but I just like to draw this just so you can understand what's going on a little bit better. And this is called the redraw step. And I find it really helps with students understanding. And that's this, right? Let me think about this. Okay. I was trying to think if I should draw the dog lifting the table, but I wasn't quite sure how to go about doing that. I'm trying to think if the dog would tip the table from this end. Let me see. I don't know if I can. Oh boy. Something like trying to draw its ear and its eye. And the dog would put its paw maybe right there on the table. And somehow, like, you know, torque the table. And because the table would, maybe it's like a small, maybe it's a small table. And that's a giant burger compared to that dog. But you get the idea, right? That maybe, and the table's leg would be standing like this, and the rest of the table, if I was to sketch it lightly, would be like that. And yeah, so maybe that's how it would work. Okay, so anyways, the redraw step is right down here where you have this burger that's sitting there, and you're gonna draw the free body diagram. But the idea is you replace FG. So you get rid of FG and you just draw its components instead, because FGY and FGX are representing FG, right? They're taking the place of FG. So Fn is still going to do its thing. Force friction, static is still going to do its thing. And then instead of drawing FG, we'll just add in a dotted force to oppose normal, and a dotted force to oppose FG, or to oppose force friction static. And what's key here is, remember, this is just for understanding. This is just to see what's really happening to the burger. But this one's also important because this one allows us to actually calculate and do the math, right? So this is more just for us to understand that this is what's happening to the burger. Okay, let's go ahead and go down here. Solve for the mass in kilograms of the Blimpie burger. I think it said it was a 300-gram burger. So that means we got to go from 300 grams into kilograms. Hopefully everybody can do this. But let me go ahead and write this out. So if we remember, we had the star right here. We had deca, hecta, and then kila, and then grams was right here at the star. So what's going to happen here is we're going to go from grams to deca. That's 1, 2, and then 3. Right there to end at kilograms, right? So we're going to move three times to the left, right? Notice what we did there. We went 1, 2, 3, all to the left, right? So that's the same thing our decimal is going to do down here. So we write our decimal in, and then 1. Sometimes this program doesn't like when I do curved lines. It wants to give me straight lines. 2, 3. All right, so the decimal is now going to be there. So we're seeing it's going to be 0.3 or 0.3, whatever you want to call it. I'm going to put the 0 in front just because I like the way it looks better. Kilograms. Okay, so now we want to get the weight of the burger. Now, we don't want the weight in pounds in our class, right? We like to use newtons for weight because weight is a force, just like anything else in any other force that's in newtons. So here's our formula where weight is Fg, and the formula for Fg is mg, where m is the mass, and this g over here isn't, like, Fg over here goes together, right? That means force, gravity. Whereas this g here represents the acceleration due to gravity, and it's 9.81 meters per second squared. All right, so anyways, long story short, we like to write all of that as just Fg equals mg. But when we plug in the mass there to solve for Fg, or force gravity, the mass we want to plug in should be in kilograms. So that's the 0.3 kilograms times 9.81 meters per second squared. All right, when we do the math there, we should be getting close to 3, a little under 3, 2.9 or so. Let's see. 2.943. Whoops. There we go, 2.943. And units here are going to be newtons because Fg is a force, and kilograms times meters per second squared is newtons. All right, so far so good. Then it says solve for Fgy and Fgx. So we just solved for this force right here, right? 2.943 newtons. So that was the hypotenuse, the purple side to the triangle. Now we want to know the adjacent and the opposite, Fgy and Fgx. So what are we going to start with here? It looks like Fgy, and it says use this cosine formula. So we're saying that the cosine of, I think our angle was 30, is equal to the adjacent, which is Fgy, divided by the hypotenuse, which was FG. Now, we also should remember that we just solved for FG, right? FG is mg is 2.943 newtons. So let's go ahead and sub that in. Multiply both sides by 2.943. Cancel, 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 cancel. Got to multiply this side by the same thing. And so we're going to end up getting not a lot of room here. I didn't do a great job designing this worksheet. FGY is equal to 2.943 times newtons times the cosine of 30. Cosine of 30 is like 0.866 approximately. It's some irrational number that just goes on forever but doesn't make any sense. So let's go ahead and multiply this. 2.943 times cos 30. Oh, I'm in radians. Make sure your calculator's not in radians. Make sure it's in degrees. If you're in pre-calc or trig, you might want to be especially careful. All right, I got about 2.549. So I'm just going to write 2.55 newtons. And that is FGY. So I'm just going to use a little highlighter there so you can see that those two are the same. Draw a line here to keep this separate. Now it says use sine theta to solve for FGX because FGX is an opposite. But I can just write this 2.55 before we do the next one up here, just so you can see what we did. So I'm saying that this is 2.55 newtons, this FGY. All right, now we want to get this last FGX side, and we'll be good. All right, so sine theta equals op over hip. So we'll just say the sine of 30 is equal to the opposite, which is the opposite is FG y. No, FGX. Whoops, sorry. Just solve for FGY. Is FGX over FG, right? Op over hip. So we already know what FG is, right? We just solved for that a second ago. We said that FG was, what did we say? Just solve for it. 2.943. So, that is what FG is. So, I kind of, let me just do it the same way I did it before, so that way it doesn't look confusing. So let's just go ahead and rewrite. This might just be. Now, sine 30 is actually a really nice number. It's 0.5. So I could have subbed that in, but I didn't yet. All right, so 2.943 newtons. Multiply both sides by 2.943. Newtons go with it. All right, cancel the 2.943, cancel the newtons, and we're left with FGX is equal to 2.943 newtons times the sine of 30. So we plug that in our calculator, which is 2.943. Sine 30 is a half, so times 0.5 is 1.4715. So I'm just going to say 1.47. All right, so I got FGY is equal to 2.55 newtons, and I've got FGX is 1.47 newtons. All right. So, okay. So we're good. Let's go ahead and add this FGX up here, 1.47 newtons. Whoops, I'm in highlighter. All right. So, so far so good. Let's see what the next step is they give us. So I'm just going in order here, right? We did 8, now we did 9. You can see there's numbers here. Now number 10. Use Newton's second law in the y direction to solve for Fn. So in the y direction, there's two forces, Fn and Fgy. Now we know they're equal because there's no acceleration, but we got to prove it with this Newton's second law with sigma Fy equals may. And so let's see if we can do the proof, right? That's the point of this question. Sometimes I have years where students will just write that down. They'll be like, oh, Fn equals Fgy. And I'm like, yeah, but you got to prove it with Newton's second law. That's what I'm really checking for. I'm checking to see if you understand how to do this, not if you can just tell me the answer, because I understand the answer is easy to just write down. So I want to see if you can write that. Newton's second law in the y direction with sigma, which is the Greek letter S. This is sigma right here. Looks like an E or something, but it is sigma. It's an S, a Greek letter S for sum. So we're summing the y forces. We know Fn points up. We know Fgy points down. This is why I'm giving them these signs. Why Fn took the positive sign, Fgy took the negative sign. The mass is 0.3 kilograms, and the acceleration, we found that, or we know that there's no acceleration because the burger is not accelerating into the table, the coffee table or whatever it's on, and the burger's not accelerating into the air. So if there's no acceleration, it's not speeding up either way, then that's equal to 0. 0 times 0.3 kilograms is just 0. And we can say Fn minus Fgy is 0. We can then add Fgy to both sides. And what we see is Fn is equal to Fgy. All right. Good. Let's go ahead and do the same thing for the x direction. Sum of the forces in the x direction is equal to max. Okay. There's no acceleration in the x direction, similar to what we just saw. And so because of that, if we go up and look at our x forces, notice I'm using the redraw to show this very easily. Force friction static points in the positive x direction, and FGX points in the negative x. The reason I like the redraw is notice where FG of x is. It's not even on the burger where it should be. We drew it down below, right? It's hanging out in that triangle, but it doesn't even, it's easy to forget, right? It's easy to forget that's there. So here I like the redraw because it shows, okay, FGX points down the incline and force friction static points up the incline. So we're going to say force friction static minus FGX is equal to the mass, which is 0.3 times 0, because the burger is not even moving, let alone accelerating, speeding up or slowing down. It's not doing that. Now it's just about to move, right? But it's like we took a picture right before it did move. So we can go ahead then and say that force friction static minus FGX is equal to 0, and therefore we can add FGX to both sides. And what we're going to get out of that is these two will cancel, and we'll get force friction static is equal to FGX. All right, so we proved what we knew, but we showed it with Newton's second law, which is what it's going to take to get the point there. All right, we're almost done. Solve for mu static. Mu static max is equal to force friction static max over force normal. All right, so how are we going to do this? Well, let's go further with these last two problems, right? I think we should get numbers here. I think actually we need numbers because we're going to use them here in a second. We know FGY is 2.55 newtons, so we can plug that in right here. And therefore, we know Fn is 2.55 newtons. Force friction static is FGX. So we know FGX, it's 1.47 newtons. So we'll take that from up here and plug that in right there. So we're saying that force friction static is equal to 1.47 newtons. All right, and the reason why we did that is because now we can just come over here and solve for this. This is going to be static max because it just begins to move. So we're going to say force friction static, which we just said is 1.47 newtons, divided by normal, which is 2.55 newtons, is equal to mu. So this is going to be mu static, actually max. All right, so notice that the units of newtons will just cancel away. And we're left with, what is 1.47 divided by 2.55? That looks like it's about 0.4. No, I was way off. 0.57. All right, so 0.576. So we'll go 0.58. So notice there's no units though. So this is just mu static max. All right. And we are almost done. Finally, what does mu stand for? It is a number that represents the ratio of the friction static max to the force normal, or you can just say a number that how best to say it? Well, we could just say what it stands for, right? And instead of trying to define it as a ratio, which it is, just say what it stands for. It stands for the coefficient of friction. Which is a number that describes that frictional ratio between force friction and force normal for any two surfaces. And it's specific to two surfaces. So the mu for, say, a block of wood sliding across a wooden plank is different than the block of wood sliding across the floor, which is a different material than a wooden plank. So mu's are based on the materials, And the reason they know the different mu's for surfaces is they just go out and test them in experiments and calculate it. All right, that's it. So hopefully that's making some sense. And if not, well, it just takes a little bit of practice, and it'll start to make more sense and get easier. All right. Anyways, have a good day.